In the previous few videos we've been looking at electrostatics. We're now going to move on to magnetic fields, and you can see the key dot points that we're going to address in this video. So the definition for magnetic fields and then how to represent magnetic fields. So the first thing with the definition, again this is from the glossary. It's a little bit of a sort of a long-winded one, largely because there's a few different scenarios in which magnetic fields can be established. So the first thing though is that it's basically just a region of space, so the region around one of these particular scenarios. The first is the most obvious, being a magnet, but we also have an electric current, and the third is a moving electrically charged object. So they're the three scenarios that we're going to be dealing with. In this video we'll start out just with the magnets, but then we'll get on to the other two in subsequent videos. So that's the first thing about this definition. And the second thing is that there's going to be some result of this region around one of those three objects. And so it's the region in which a magnetic force acts, and it's going to act on any other magnet. So again, listing out these three things now. So any other magnet, electric current, or moving electrically charged object. So there's going to be a few scenarios here that we'll need to address, a few ideas and concepts that we'll have to tie together. Considering that we could have two magnets near each other, or a magnet around a current. So there's a few different things that we'll need to address as we go through this subtopic on magnetic fields. Now, similarly to electric fields, we can represent magnetic fields using magnetic field lines, and there's a similar definition for magnetic field lines, or similar explanation I should say. So magnetic field lines show two things the same way that electric field lines do. The first is that they show the direction of force. So field lines always show a direction of force, but in the case of a magnetic field it's on a singular north pole. Now I need to make a point here that a singular north pole doesn't actually exist. So we're treating it as though we've got this small north pole that we can use to identify what force would be exerted on it, but in reality you can't have a north pole by itself. You're always going to have a north pole and a south pole together, but the definition or the explanation of the magnetic field line, we're going to use that construct as though it does exist. The second thing, as field lines always do, is that they show the strength of the field, and similarly to electric fields, I'll just make the note in brackets here, that's related to the spacing of the field lines. So the further apart they are, the weaker the field. Now if we look at the magnetic field that exists around a magnet, so we're going to start off just with a simple bar magnet scenario. Hopefully you've all experienced the magnet before, so something that you might put on your fridge, or you may have come across it in junior science classes or in primary school even. So basically we're just going to look at what happens when a singular north pole is placed around this region, and it ends up being a fairly intuitive sort of scenario that when you start to place a north pole anywhere around this region, you'd start to see this sort of field being produced. Now we can have a look at a few ways of representing this in class, a few demonstrations and things. So there's some really good ways of visualizing these fields, because in the end these fields are not they're not sort of real things as such. It's not until you actually place an object in the locations that we're indicating here that they would experience a force. But if we were to imagine what would happen, then the field would look something like that. Notice that I haven't drawn it off in all directions. I've just sort of limited it to the space that I've got available there. But you can see that the field lines, there's a particular shape about them that's important to be aware of. So I'll just note some things down the bottom here. The first thing is that around magnets, field lines originate at the North Pole. So it looks like that's where they start. And then they will terminate at the South Pole. It sort of makes sense. If you've got a singular North Pole, then it would be repelled from a North Pole, and they'd be attracted to the South Pole, and so we get that that shape going from the North Pole through to the South Pole. To make a comparison to electric fields here, imagine instead of having a North Pole, we replace that with a positive charge, and at the South Pole we had a negative charge. If we were to draw the electric field lines in that situation, they would look the same as the red lines that we've currently got on the screen there. So North Pole is similar to a positive charge. It's not actually a charge, but it acts similarly to a positive charge in terms of the field lines being directed away from it, and South Pole acts similarly to a negative charge in that the field lines are directed towards it. Just want to be clear here that North and South Poles are not charges, they're different things. Now the second thing that's important to note about magnets is that if we were to take that bar magnet that we've drawn above and split it into two, as I mentioned, we can't actually get a singular North Pole, neither can we get a singular South Pole. Instead what we'll see is that we'll end up forming two magnets. So two smaller magnets are produced, and the field lines would then be similarly structured, so out of the north and into the south. And so we're not going to see those singular poles, and we'll have instead two smaller bar magnets. Finally, the last point to make that'll seem a little bit strange to say it considering what we've just seen with a bar magnet. Magnetic field lines don't actually originate and terminate in the same way that electric field lines do. So magnetic field lines form closed loops. So while we've got a bar magnet where it looks like the field lines come out of the north and into the south, what we really have for a bar magnet is that the field lines will start to actually travel the opposite way through the magnet itself. So inside the magnet we get field lines that run from south to the north. We can't actually experience those inside the magnet because it's a solid object, but it's an important point to make because it will relate to some of the aspects that we'll be dealing with in the coming scenarios, so linking up with the ideas of electric currents and moving charged particles. So we'll take that a step further in the next video where we'll look at the field lines that are produced around an electric current.